All right, good morning, everyone. So let me reassure students, as long as you don't see a Pearson quiz or quiz submission for Pearson, there is no quiz. I always announce in class. Plus, I post an announcement on the Canvas webpage. So if you don't see an announcement and there is no email, that means that there is no quiz. So I apologize for the dates. The dates were preset for the Canvas submissions. But as long as you don't see a posted announcement and don't see a Pearson submission, then there is no quiz until then. Having said that, quiz 5, I'm leaning towards either Wednesday or Thursday. If it's Wednesday in class, it'll be proctored live. If it's not, that might be Wednesday and Thursday, and no live proctoring. So I haven't decided yet. So quiz 5, the earliest quiz 5 will be is Wednesday. Okay, and we'll think about it and decide by the end of today. All right, so let us continue with logic gates. All right, chapter 4. We stopped here, NOR building block. Okay, so we looked at the 3 fundamental gates, which is the NOT, the AND, and the OR. And then if we combine the NOT and the AND gate, we get the NAND gate. If we combine the NOT and the OR gate, we get the NOR gate. Now, everything that we have learned so far falls under the umbrella of combinational logic circuits. Okay, combinational logic circuits. We are combining multiple functions, multiple circuits, and we are combining different circuits in a variety of combination to obtain our desired output. Hence, it's known as combinational logic. Now, before we talk about this, what I want to state is there is a slide back here. De Morgan's laws, right? De Morgan's laws, it's not just simply for logic design, it's mathematical theorems, mathematical theory. Anyone have a question? Okay. So it's mathematical theory that we use for logic circuit design. This mathematical branch is known as Boolean algebra. It's named after the mathematician George Boole. So it's known as Boolean algebra. Named after George Boole. And so there are a few things that might be different, but most of it is similar to our to the math and the algebra that we studied in high school or in middle school, if you will, which is the OR function is a summation, meaning it's A plus B plus C plus D, so on and so forth. So it's an addition. The AND function, we say A and B and C and D, is similar to the multiplication, right? We've seen that. So De Morgan's laws, and this is again a recap of last class, are basically 2 laws that we can apply to resolve circuits and to simplify them, where you can convert an OR function, AND function to OR and vice versa, or you can take an OR function and convert it to an AND function. Okay. So you can convert from AND to OR 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 to AND, from addition to multiplication, multiplication to addition. I just wanted to cover this before we moved into the larger equation. Applications of of these logic design, we use this in everyday life. One of the most common examples is basically your thermostat. We set the temperature on a thermostat at a certain level. At a certain level. Let's say it is a AND gate. Okay. It's an AND gate. Now for an AND gate, we know the output will be high or logic 1 only when both inputs are logic 1. That AND is multiplication. So if it's 0 and 0, output is 0. If it's 0 and 1, output is still 0. 1 and 0, output is still 0. 1 and 1, both inputs are high, both inputs are at 5 volts. That is the only time the output goes to 5 volts. So let's say this is your set temperature and this is your measured temperature. Okay, set temperature, measured temperature. Your set temperature is 70 degrees. And your thermostat, let's say you're using it for heating. So if the set temperature is set at 70 degrees, and let's use logic high, for instance. So this is 1. If the measured temperature is above 70, then the input, if the set measured temperature is above 70 degrees, then the input to the measured line is 0. Then the output is also 0. Okay. So let's do that. Set temperature 70 degrees, measured temperature greater than 70, then output is 0. Now your measured temperature goes to less than 70. We design the circuit in such a way that this sensor goes high, 1. And the output goes to 1. When the output goes to 1, it signals the heater to turn on. Heater to turn on. AND gate, one input is set to set temperature, the other one is measured. Output turns high when both inputs go high. And again, this is a very simplistic example. We can use a combination of gates with multiple inputs to actually change the output according to our desires. Does that make sense? Example makes sense. Logic design. So this is a 2-input AND gate. We could perhaps use a 2-input NAND gate. If all we have with us for designing the circuit is a NAND gate, we could use a NAND gate, and then we could switch out zeros and ones as we want, right? An additional setting that we perform is like our HVAC unit can do both heating as well as cooling. If that's the case, if it's a 2-in-1 system, then we need another line to go either low or high, depending on our setting mode, meaning whether we wish to heat or whether we wish to cool down. And we could set perhaps heating to 1 and cooling to 0. So that would add a third input into our system. So we could say if the signal coming from the third input, A, B, and C, if C is 0, then it's cooling. If C is 1, then it's heating. And then you connect that into your AND gate or your NAND gate, as the case may be. So depending on the features that we want, we would design such a system to have as many inputs as possible. Modern day thermostat, the smart sensors that we see, they have wireless sensors that you can place in every single room. So if the room vents are far away from our HVAC units, each one of those sensors will send a signal that can be translated as logic low or logic high, and will either turn on or turn off your heating or cooling. So the more features you want, the more inputs we have, the more complicated the design becomes. And to simplify those designs, we use Boolean algebra and then De Morgan's laws. Okay. 10-second pause. Think over that. Let me know if you have questions.
Yeah, I had a question.
Yes, go ahead.
The thermostat in your example there, is that considered what logic gate is that considered?
It wouldn't be, well, what do you mean? Which logic gate, as in like which gate are we using? And
Right.
or is that what you're asking?
Yes.
Okay, so the question being asked is what kind of gates can we use? And that is up to the designer. NAND is pretty much the most common one that is available. So if you're designing a system from scratch and we have the option of choosing whichever gate we want, we can choose any gate we want. This system right here can be designed with any gate we want. We can use an AND gate, we can use an OR gate. The only thing that would change is the algebra. Is the logic would change depending on which gate we wish to use. And that is the whole point of using these laws and Boolean algebra. So if we only had an AND gate, we would implement functions with this. If we had an OR gate or a NOT gate, we would implement functions with this. Does that answer your question?
Yes. Yes. Thank you.
All right. All right. Any other questions? Okay. All right. NAND building block. Oh, one more point. Actually, this is kind of important. So we are translating from AND to OR and OR to AND, vice versa, right? We can do so. The most important thing is right up here. You have to invert the inputs. Okay, invert the inputs. So if you were to explain this, if we wish to go from A and B and implement a OR operation instead of an AND, we would invert both inputs, and perform an OR operation, and then we invert the output. And that's what you have at the top. Again, you have two inputs, A and B, and instead of using an AND gate, we like to use a OR function or an OR gate. Then we would invert both the inputs, convert it into an OR function, and then invert the output. Three-step process. Okay, three-step process. So invert both inputs, then perform the OR function, and then finally invert the outputs. And the same thing goes for the second law. If you have an OR function and you wish to convert it to an AND function, you have A plus B, invert it, and then change the OR function to an AND function, and then finally you invert that output. And that's how you obtain the right side of that equation. All right, let's take a 10-second pause. Let me know if you have any questions. Make sense thus far? Okay. All right, so we had the XOR, exclusive OR, and exclusive NOR. And then we looked at the two slides of NAND building blocks and the NOR building blocks. And that's what is being shown here. Right? You wish to do a OR operation. If you wish to do an OR operation, we can use De Morgan's laws to first invert that input, right? Invert that input. And then we sum it up. So this is an, and this is an AND function. But because this is an AND function, and this is the inverted AND output, it becomes A naught and B naught, the whole naught becomes A plus B. Okay. The result is an OR function, A plus B, or A or B. And same thing when we have a NOR building block. You can take a NOR gate, invert it, and feed it back into a NOR gate to obtain an A and B output. A and B. Okay, A and B. So you can perform any function using any kind of gate. That is the whole point. You can perform any kind of function with any kind of gate. All right, combinational logic. So the first thing about combinational logic is that it does not have any memory, in the sense that the output is only present when the inputs are present. If there are no inputs, there is no output. We will see later in sequential logic different circuits where the output will be maintained even if there is no input. Okay, and we say that those circuits have memory and these ones don't. So the memory is simply in terms of the input, not in terms of the power supply. Again, we go back to chapters 1, 2, and 3, where we had biasing voltages for our circuits. A transistor amplifier, we apply a DC bias, meaning a DC voltage is applied. So we set the DC operating point of that transistor circuit. And then the input arrives. The input is an AC signal, and that AC signal will then change the DC biasing outputs. So the DC bias would be the power supply. The AC would be the input signal. So in these logic gates, the input signals will cause an output to appear. If the input signal is not present, the output also will disappear. The circuit could have power supply and the DC bias, that is fine. But as long as nothing is applied to the input terminals, output is 0. And so the circuits do not have any memory. No output without an input signal. Basically, when we talk of logic circuits, we don't consider the power supply at all. It is implied that the power is already present. So if you're talking about applying an input to a logic gate, we assume that the power is already present. Okay. So if we wish to implement this function, and again, this function could be anything, right? Could be anything. If we could be like a sensor in a car, in a vehicle, could be your temperature settings at home, could be anything. Basically, it takes multiple inputs and provides a desired output. So if you wish to implement this, first we identify the output is F In the input side, we have 5 inputs: A, B, C, D, and E. 5 different inputs. 5 different inputs. The simplistic example we used in the previous slide, the thermostat, we had 3 different inputs: set temperature, desired temperature, and the mode of operation. Typically, HVAC systems will also have, mode is off and we just want to run the fan. And that could be a 4th input. Placing different sensors in different parts of your residence, that would be multiple inputs. And so that would be another, if you have 5 rooms, that's 5 more inputs. So a simple system can become complicated very quickly. And that's why we have Boolean algebra and combinational logic. All right. So if we wish to implement this, we'll take it one at a time. Yeah, the first term is A and B not and C. Second one is A and B and C. The third one, long, you have 2 OR functions, C plus D and D not plus E. And then both of them are connected together via an AND function. Okay. So let me switch colors. All right. So here it's primarily an AND function. Right here. So A, C would be an AND function. And then we have A, B, C, again, an AND function. And then here we have an OR and an AND function. Okay, OR and AND function. All right. So if we wish to implement the first 2 terms, we need a 3 input AND gate. 3 input AND gate. And let me point out something else. Because I've already done this, I know how much space I need. So I'm going to draw it below the figure right here. So let's see. AND gate. All right, for A, B, and C. For A, B, and C. Actually, let's first draw out the 5 inputs. So you got A, B, C, D, and E. Now, ABC goes to the second AND gate. So let's do it this way. A, B, C, D, E. That's A. B. And that's C. So the output of the second gate is A and B and C. Simple enough, right? Again, let's look at the equation. Second term, A and B and C. So we can implement it using a 3 input AND gate right here. Okay. The first term is A and B not and C. So A can go directly into the input. Okay, that's A. And B needs to be inverted before it goes in. So I'm going to draw this out. Let's see. Let's draw it out here. Inverter gate. And here. You can see the line is crossing over. So when we draw this kind of logic circuit diagram or logic design, we use this. Anywhere we have a connection, we're going to mark with a shaded dot. If there is no shaded dot, that means there is no connection. Okay. And of course we have C. Right. A, B, and C. So the output of this one is then A and B not and C. All right, let's take a pause. Let me know if you have any questions. Okay. Any questions? Does it all make sense so far? Right. Then what's the next? It's C plus D and D naught plus E. And then the output is fed to an AND gate. So let's draw this closer. And let's do it this way. So this is C plus D. So let's extend it here. So this becomes C plus D. And then we have D naught plus E. So D naught and D naught plus E. And this is D naught. Okay. C plus D and D naught plus E, the outputs of which are fed to an AND gate. Thus, here we obtain C plus D and D naught plus E. So we have our three terms. Okay. This was the first, second, and third. So this is 1, 2, and 3. And all 3 are then fed into a 3-input OR gate. So 3-input OR gate gives me F. So then, well, let me cross this out. Okay, here the output is C plus D and DR plus E. All right, let's take a pause, write it down, think over it. Let me know if you have any questions. And C plus D, DR plus E, C plus D and D plus E, and then everything is summed up in F. Okay. 7, 8. Any questions? Any questions at all? Does it make sense? All right, so then again, reinforcing the point about why do we need to know combinational logic circuit design, Boolean algebra, De Morgan's laws? Well, here's the thing. How many gates do we see? We got 1, 2, 3, 4, 5, 6, 7, and 8. A total of 8 gates, plus there are 3-input gates, 3-input AND gates, 3-input NOR gates. Let's say we had a IC chip that was just all NAND gates. Okay, and that's how pretty much most circuits are built. Let's say it's all NAND gates. We need to write a program that would create this circuit or this logic using only NAND gates. Only NAND gates. And so then the number of gates increases. Okay. If you have like 1,000,000 gates available to you, then you don't care about efficiency. Right? If you have 1,000,000 gates in that IC chip, 8 or 9 gates doesn't matter. If you implement each one of these, a NOT function and the NAND gate and the AND gates with like multiple NAND gates, it's fine. But if your circuit design, and this of course it happens in real life, is if your circuit design requires, 1,000,000 gates, and all you have is a chip with 1,000,000 gates, you need to ensure that it fits perfectly in there. Otherwise, the chip's not going to work when you try to program it. And that's the point of combinational logic circuit design. Okay, we try to reduce and make the design more efficient. Plus, the longer and the larger the circuit design is, the more issues that can crop up. Okay, which is again, it's all part of circuit design of an EE engineer, EE and CPE design engineer. Okay. And the way it ties into electric circuits, each one of these gates is made of multiple transistors. Okay. Multiple transistors. All right, so that was combinational logic. Many of the circuits that we use in everyday life are sequential. And that's where the name sequential logic comes in. And sequential logic, of course, as the name suggests, is so called because the circuits work or function in sequence. Okay. We have all heard of CPU frequencies, right? You take a chip processor and we say, okay, run at like 2 gigahertz or 2.5 gigahertz, 3 gigahertz speed. What is that speed? That is the clock speed that governs all functions in that system. Okay, that frequency is the speed at which it operates. In sequential logic, what happens is you have either a square or a rectangular clock pulse, a square or a rectangular signal or function, and we call that signal as a clock. Okay, and that clock will trigger a response from your system. So basically, let me write it here. A square or rectangular AC signal, it is referred to as a clock signal. Clock signal. And this clock signal will triggers a response from the system or the circuit. Okay. As a quick refresher, frequency is 1 over t, the time period. It's the number of cycles per second. What is the frequency of the power outlet? The regular power outlets that we use in this country, what is the frequency? Should be common knowledge. You should go back and change your grades for 201 if you can't answer that. Seriously? It's on every adapter, every appliance, every piece of electronics or electric appliance that we ever use. 60 hertz, 120 volts, 60 hertz. I should go back and change your grade for 201. This is also not an engineering thing, okay? It's just a general knowledge thing. As I said, if you look at any wall adapter, any mobile phone charger, tablet charger, any laptop adapter, any electric appliance that you use, you plug it into the wall, that power outlet is 120 volts, 60 hertz frequency. 60 times a second, it goes and cycles between a positive and negative peak. Anyway, so that's the frequency. When it comes to electronic circuits or digital electronic circuits, this clock signal has a frequency, and this is also known as the CPU frequency that I referred to just a few minutes ago. Right? Every smartphone, every tablet, every computer, every desktop, every laptop has a central processing unit. That's the main chip that controls everything. And the operating frequency of that CPU is from the clock that governs it. This is a fun fact. You know how if you take the exact same, if you buy the exact same computer, whether it's a desktop or a laptop, and you are trying to customize it by selecting a CPU with higher frequencies, and the higher the frequency, meaning the faster it can operate, the more money you have to pay. Intel and AMD, the ones that make these processors, there is no difference in that chip when they build it. Absolutely no differences. It's the exact same chip. They not design, but they use or they select a few chips to run at a lower frequency. Then they select a few chips to run at a slightly higher frequency. They test them and see if they're functioning correctly or not. And then they sell them at different prices. That's why overclocking, how many of you have heard of overclocking? Right? Overclock. That's why it's possible to overclock, is because the chips are capable of running at higher speeds. There's nothing else to it. The chip is exactly the same. It's just that when they test it out, they keep certain batch to run at lower speeds and certain batches at higher speeds. That is not to say that all chips would work at a higher frequency, but essentially all chips are the same. Anyway, coming back here, we have a square or rectangular pulse, rectangular AC signal. Here is the high and here is the low. So this, where the voltage is at high, is logic 1. When it's 0, it's logic 0, and so on and so forth. So it alternates between high, low, high, low, high, low. And depending on what our circuit is, the function would change. So sequential logic is important because it allows us to control how and when the circuit will operate. Okay. Then let's look at flip-flops. These are, again, building blocks for larger digital circuits. So flip-flops are building blocks for larger digital circuits. Okay. So the rest of this chapter, we are going to look at sequential logic circuits. You know what? Since it's the end of combinational circuits, let's take a break now. I'll end this lecture for now. Let's take a break. And it's 10:52, 10:53. So let's meet back at 11. All right, and then we'll go into sequential logic circuits.